Okay, good to see you back. I'm gonna continue discussing the syntax of Numpy and later on SciPy. So we were discussing how to manipulate data in Numpy, and the point is we have potentially large arrays. Numpy arrays in data. Currently, this data contains temperature. Temperature is read by this Stockholm temperature in from year 1800 to 2011. So it's a lot of data, and we want to manipulate this data somehow. If we take we have a two-dimensional array, of course, and if we took just one index here, we're going to get, of course, the first row. If we take if we write here whatever 0, it means whatever I, some integer, we're going to get, of course, the row, no, the column, and then if we specify with this double dot, we can specify beginning, the end, and the spacing. So we discussed this several times. This nomenclature is that if you have a double dot in between, then the first integer means beginning, which can also be negative. Negative means start counting from the back. Then the end, and if the integer is omitted, it means that the end is default, which means in this case to the very end of the array, and then the spacing is this number 365. So in this case, of course, this means that we are going to look at 3,650 last items. We are gonna take every 365th entry, counting from the back, and we are gonna go all the way to the end. So as a result, we are gonna be printing last couple of years. So last 10 years, isn't it? Okay, so that's what we repeated last time. So another thing which I wanted to explain is so-called fancy indexing. So fancy indexing means that instead of giving just a simple integer to a data to take to index the data, you can give an array rather than simple integer. Okay, so normally, of course, we would just say you would say data. Whoops. You would say data of two numbers, 3, 4. Okay, so but if we give or 3, 0, okay, so it means just one item, but we can give here an array of stuff. Okay, an array of items, integers, and this means they don't take just the one row, but take several of them. Okay, and we can specify which one. So in this case, we're going to take the 0th row, 365th row, 2 times 365th row, 3 times 665th row. Okay, which means that we are going to take, because the year has 365 entries, we're going to just take the first day of each year. Okay, first day of each year. Of course, we could take also anything here, which means that we are taking now first day of each year and all corresponding data. So basically all corresponding columns. Okay, or we take just the first column, which is just the year. Okay, so this fancy indexing tells you, shows you how to pick out particular rows. Okay, particular rows that you decided that you need. And how to pick out the data is actually very useful. and very important. Therefore, there are several ways that are provided in Numpy to pick out the data. Okay, so one, for example, is to use so-called mask. Okay, mask. So what does mask mean? Well, instead of giving a set of numbers here, you could give a large array which contains true or false. The array size needs to be exactly as long as the number of rows. So it has to be identical to number of rows, but it can be either true or false. And as you can guess, if this mask is true, the data is returned. If the mask is false, the data is ignored. Okay. So let's say that we want to create a mask for a particular year, 1973. Okay. So let's say that we want from all this data, just pick out the data that corresponds to the year 1973. Okay. So how would we do that? Well, here's an example. First, we're going to say very simply that data of the first column has to be the first column has year, and this year has to be bigger than 1973, isn't it? So in this case, we're going to see that up to 1973 everything was false, but after 1973 all the entries are true. Okay, so that's simple. So at the same time, we can also say data of 0, and we say that this is less than 1974. Okay, so if we do that, then you can also understand what's going to happen. So up to the year 1974, everything is true, and after that, everything is false. Okay, so that's obvious. And now we just need to combine these two. So if we want to combine these two and pick exactly 1973 out of this, how do we do that? Well, we need to take logical AND of the two arrays, isn't it? Logical AND of the two arrays. Okay, so how do you do that? Well, simple. You call there is an array. There is a function which is called logical AND, which can take logical AND between two arrays element by element, and this creates a mask. And now this mask, if we print it, yeah, actually here we can print it. We can print it. You will see. No, what I wanted to do is to print mask. Okay, so mask has most of the entries are false, but there are of course some entries in somewhere in the middle which are true. It's hard to see them right now from printing, but the point is that mask has true and false. And now if we use this as an first argument of the slicing, then we will pick out only the data which corresponds to 1973. Okay, so now we are printing only the first column, and the first column definitely shows you 1973. So we're just checking that this is correct, that the code works. But if I take column, let's say 3, then it displays me the temperature in the year 1973, isn't it? These are all the temperatures day by day of this year, 1973. Okay. So if I want to save this data from 1973, I assign this to some variable T1 at 1973. And if I want to calculate the average temperature in 1973, all I need to do is to sum this data and divide by the length, which is probably 365. And I get the average temperature to be 7.4 degrees. Okay, so this demonstrates how easy it is to use slicing to do something in Python. Okay, how are we going to do the same thing in C? Well, typical way to do this in C is to loop through the array, through the entire array. You have a do loop, for loop actually, for I is 0, I is less than n, plus plus I, and then you're going to have an if sentence. If year is between 1973 and 1974, then use the data, isn't it? Now, we don't do this in Python. Why? Because any do loop in Python would be extremely slow. It would work, but it would be extremely slow. So the idea is, instead of using do loop, you have to use this provided functionality of slicing. Okay, and there are several ways to do that. As I said, one is to use fancy indexing. Another one is to use mask. Now, to bridge between the two, between fancy indexing and mask, you can use so-called where function. So what does where do? Where? I mean, it asks which indices are true or false. So if you do where on the mask, okay, it will give you a set of numbers which correspond to the indices which were true. Okay, so 1973 is contained in the row 63,187 to 63,551, it turns out. Okay, and now, of course, once you have this indices, now you can use these indices through so-called fancy what is it called? Fancy indexing, isn't it? So we're going to use now fancy indexing to get exactly the same thing that we did before. Yeah. So by the way, if we don't want to have anything printed, we can append here semicolon. Okay. So if we want to print out, then semicolon. Right now it doesn't print anything. But the point is that whenever you want to omit printing, you can add semicolon. Why does it do that? Well, it turns out that if you want to have two statements in one line, so let's say A is equal to 1, but B is equal to 3, normally you have to write two Python statements in two Python lines. You can't have it in the same line. So for example, this would be an error. You can't do that, isn't it? However, there is a trick. You can put between two different statements a semicolon, and then this is valid code, and it does correct thing. Okay, so semicolon is used to kind of delimit the lines. Now, if we do this, then we are saying, well, in addition to the first statement, there is an empty line. And because there is an empty line, there is no printout, because Jupyter would always pick the last statement and then use this as a printout, doesn't it? So therefore, when you put a semicolon at the end, it's like you don't want to have a printout in Jupyter. Okay. Anyway, so what we did here is we took the indices, which we obtained through so-called where command, and we now took the slice out of data, which is again data from 1973. Okay, and yeah, so now if we look at the shape of the two types of data, we see that they are very similar. So both are 365 in length, but there is a tiny difference between the two. So the data which we got with the mask is actually just a real one-dimensional array, while the data that we got through fancy indexing is kind of two-dimensional array with the size 1 times 365. Okay, so it's kind of the same or similar, but the difference is that when you use the second data that was obtained through fancy indexing, you always need to take the zeroth component, isn't it? The zeroth, what would that be? The first, I guess, row. isn't it? So if you take the first row, then you get exactly the same thing. Yeah, except that yeah, this is actually wrong. So it shouldn't be third component. There should be the third component, not the zero component, because it gives you the wrong temperature. Yeah. So if you take here entry 0, then we're taking just the year. We have to take entry 3, which is actually a temperature, isn't it? And then we take the 0 component of that, and then we get the average of the temperature, which is 7.4, and it's the same as what we got before, 7.4. Okay. So I want to demonstrate that there are two ways to do to access this particular data, either through fancy indexing or through this true and false array. Okay. Now let's say that somebody asks you to calculate mean monthly temperature for each month of the year. Okay. So how would you do that? Well, how do you do this in C? Well, I guess double loop. So the outer loop is probably going to be over all months, and the inner loop is going to be then over all data, and making sure that every time you just kept only the particular months that you're interested in, isn't it? So in C, at least I would probably, first idea that comes to my mind is a double for loop. Now the trouble is the double for loop is way too expensive in Python. You don't want to do that. Okay. So how would you do it then? Well, slicing. I want to demonstrate this with using slicing. So what do? Well, let's say that you want to get the data that corresponds to February. Okay, so what is the data that corresponds to February? Well, we take the first column, isn't it? We take the data with the first column, and we say that this data with this first column has to be equal to 2, because 2 is, well, it's the month, isn't it? 2 means February, doesn't it? 1 means January, 2 means February. So this will create 0 and 1, true and false in such a way that all the data that corresponds to February will be true and every other data will be false, doesn't it? Okay, so we're gonna get a mask that will pick out February's. Okay, mask that picks out February, and then it's easy. Once we have the mask, we use this as a first entry in the to pick up the rows. Okay, and then we take the temperature, which is the third column. Okay, and then we take mean of this. Okay, so this gives you the average temperature of February. Okay, of course, this is way faster than writing a loop over data. So in other words, in this first line, we created a true and false array, or basically array that contains a mask, true and false, in such a way that only the data that corresponds to February has true components true, and the rest of the data has components false. And then we use this with this so-called mask as a mask, and then we do the mean. Okay, so we know how to do it for February. Now we can do it for every month. Okay, so in order to do it for every month, we still need to write a do loop, but it's going to be do loop only over months. So we write the do loop like this: for months in range 1 to 13, which means month can be 1, 2, 3, 4, 5, up to 12, isn't it? Less than 13. Okay, so we are looping over all months, and then instead of writing here the mask to be equal to 2, we are going to write that mask is equal to month, isn't it? So we write here, when we create the mask, we say data of 1 is equal to month. Okay, this part here will create our mask. Then we immediately use this mask inside the data, and we pick out the column 3, okay, which is the temperature. And then we don't even actually create this array. All we do is we calculate mean of that data, okay? So we are taking slices, and we are then giving these slices immediately to a function. So actually the data is not even being, these huge data are not, we're not even making local copy. We are just giving masks on that data. That's extremely efficient. It's way more efficient than any do loop that you could write. Okay, and you see it's done in microseconds, very quick. Okay, now we can display this monthly average. So we can use so-called bar function. Bar function is similar than plot, except that it prints this bars rather than a line. And the vertical axis is just integer from 1 to 12, and let's see, this is horizontal axis. Horizontal axis are integer from 1 to 12, and vertical axis is whatever we produce, monthly mean, isn't it? Mean temperature for each month. And then we added here the X label and Y label, which just gives this axis the name, month and average temperature. Okay, so basically with just one line, we managed to create monthly average temperature, and then we just 3 lines we managed to fancy plot that. So that's how powerful Numpy is. Okay, so this is all about slicing. Now a little bit of linear algebra, and then we are done with Numpy. So the linear algebra, of course, is something that we always use this low-level Fortran code that was produced in University of Tennessee, and it's called BLAS and LAPAC. There's also a C code, which is called C BLAS, but I think most of the time we're using actually Fortran code, Fortran BLAS. And it's way more efficient than anything that you can, of course, develop in Python yourself. So in order to test this, we're going to create first a random matrix, 3 by 3 random matrix. So which we now remember how to do is just we're going to call a random rand 3 by 3 3, which creates a random matrix of 3 by 3. Okay, then we print this matrix, and then we're going to multiply A times A. Okay, so we have first matrix, some random matrix, and then we print A times A. Now, what does this A times A do? What is that? Well, it doesn't do what naively would expect. So A times A, if it's a matrix, I would expect this to be a matrix product. But you have to remember that if this is not a real matrix, but it's just an array, then every time you write any operation here, it will be element-wise operation. Okay, so for arrays, arrays are more general than matrices. So Numpy, we didn't tell the Numpy that this is actually a matrix. We just said to Numpy that this is a regular array. And whenever you use any operator between regular arrays, it's always assumed to be element-wise. Okay, so A times A is really just an element-wise multiplication. So it's 0.6 times 0.6, 0.69 times 0.69, and so on. Okay, so each component multiplied by itself. Now, however, if you want really a matrix product, then there is a routine which is called dot. Okay, and dot is actually pretty general in the sense that it can multiply two matrices. It can multiply matrix times a vector. It can multiply tensor times a tensor, and so on and so forth. Okay, so now the way this dot actually works is interesting because it always from the first tensor, it always takes the last dimension and iterates over the last dimension. Okay, of course, if it's two-dimensional array, that means that it's dimension 2. But from the second array, it takes it iterates through the dimension which appears before the last dimension, so n-1th dimension. So the first one always the last dimension, and the second one always from last -1 dimension. Okay, and of course for two-dimensional arrays this works correctly. So you take the second dimension from A and the first dimension from the second matrix. Okay, so that's how dot works in general. So basically, it works on any n-dimensional array, but it will give you an error if the dimensions of the two if the length of the two dimensions that one needs to trace over are not equal, because then you cannot do dot product. Okay, so what I want to say is the following. Let's say that you have I, J, K. Let's say that A is like that. Let's say we do A times B, and let's say that A is a generic tensor of the third order, and then B is also a generic tensor of let's say third order. Then we're going to have L, M, N, and now we want to trace over some index. Now it turns out that this is going to be traced over that index and that index. Okay, so which means the last in the first array and the one before the last in the second array. Okay, so that's how it's going to be done. In general, this is dot. Okay. Yep. So, now it doesn't work because B is not defined, but A times A works. Okay, so this is just a matrix product of A times A. Now we can construct also a vector, some random vector of the length 3, and then we can use dot product also as a matrix times vector or vector times vector, and both are kind of obvious. So matrix times vector produces a vector, and vector times vector produces a number. So tensor product. Now, we can also multiply vector times matrix with times, but the point is that this is not what you expect to be. So it's not a real dot product. It's basically we take first number from vector and multiply the entire array, the entire first row with the first number, and then we take the second row, the second number from V1, and multiply the entire row with this number, and so on. So basically, this is something else than the dot product. Okay, it's kind of element-wise again, but between two-dimensional array and one-dimensional array. Now, many times we don't want to use this function dot. Okay, why? Because it's kind of the code looks ugly. Okay, and we might not want to use that. So as a result, Python provides something which is called matrix class. Okay, so you can produce from an array matrices, and once you have matrices, then operations are kind of nicer. I mean, the code is nicer. You can use operation like times, and it will be actually a matrix product. Okay, so in other words, if you want to use Python, if you want to write fancy code or nice code, so it looks nice for linear algebra, you can use a special type which is called matrix. Now, the small warning here is that these matrices tend to be slightly slower. The code tends to be slightly slower than when you use dot on arrays. So if you really want to have speed in your code, then don't use matrices, use the dot. But the code is a bit less nice, okay? But if you want to have a nice code, then basically create matrices, so the use type matrix. And once you do that, well, then n times n is indeed matrix product. So we should probably check that this is the same as dot a dot a. You see, here we have dot a output, and here we have m times m output, and they are the same. Okay, so dot on arrays does the same thing as times on matrices. Okay, now
hi, Professor.
Yes.
Sorry for interrupting. May I ask a question? So
Yes, sure.
I remember so if A and B are regular Numpy array, you can just use A at B. At is the at symbol. Use it as a matrix multiplication, right?
There is something, yes. I think it's at. And
yeah.
No,
at
A.
A.
Exactly. Yeah. That works as well. Yeah. This is in Python.
Yeah, but why don't you use that? Is there any issue of speed or like stability?
Speed.
Okay.
Speed. So dot beats everything else.
Oh, okay. I see. Yeah. Okay. Thank you.
Yeah. But the point is that for matrix product is special. So they provided this at thing. But the problem is that for many other things you don't have functionality. So for example, Hermitian. You want to take Hermitian conjugate, okay, of A. It says, I don't know what to do. Okay, but if I use M, then it works. There are many other things, but this is one example. Okay, Hermitian conjugate. You need this a lot. I mean, in quantum mechanics, isn't it? Hermitian conjugate. And it's useful. Yeah. So now M times V is of course matrix vector product, and well, here you have to be careful if you have matrices that V times M will not work. Okay, because V is a matrix and M is a matrix. You need to use V transpose because the dimensions have to properly align, doesn't it? And if you don't transpose, you don't get the right thing. And of course, V transpose times V is the inner product, which still gives you a two-dimensional array with the size 1, 1. Okay, so it always gives you a matrix back. All these products gives you matrices. But of course, matrices can be just 1 times 1. So what else is provided for matrices? Well, there is dot T or transpose. They both work. So if you want to do either A dot T, it gives you a transpose matrix, or you can do transpose A. Of course. Now this works both on matrices and on arrays. Now Hermitian conjugate, as I showed before, M dot H works, but A dot H does not. So, however, there is something which is called conjugate A, and that works. Conjugate A. This works both on arrays and on matrices, but conjugate is not the same as Hermitian conjugate. Okay, so AT conjugate, however, is Hermitian conjugate, doesn't it? Because you have to transpose and conjugate at the same time. So if you have arrays, I guess that's what you need to do. It doesn't look quite as good as H. And then, of course, you can always take real and measuring part of an array if you have it. Okay, so this is all about matrices. Now, there are other linear algebra. There are, of course, a lot of linear algebra routines, and we are not going to go through all of them, but we're going to just introduce a few, which are the most commonly used. These routines are inside linalg, I think, from Numpy. Yeah, this is one confusing thing. So you can import this linalg from either from Numpy or from SciPy. Turns out that they exist in both. Now, I think that currently it is encouraged to use linalg from Numpy rather than from SciPy, but both work. I mean, at least until recently, I was always using SciPy, linalg from SciPy, but now that they seems to be ported into Numpy, so and encourage us to use this. Okay, so we first import from Numpy, import linalg, and then we can use determinant is determinant, of course. Inv is inverse. Eig is gives eigen system, so basically eigenvectors and eigenvalues. Eigvals gives eigenvalues, and Eig gives you eigensystem for Hermitian matrix. And in addition to this, there is also linalg Eigvals H. So whenever you add H at the end, means Hermitian. Now, if the system is, if the entries are not complex but just real, then H means symmetric. Okay, it's symmetric matrix. So it will figure out that if it's real, then means symmetric, not Hermitian, not Hermitian symmetric. Then there is SVD, SVD decomposition. Solve means solve system of linear equations, and then Kolesk is Kolesk decomposition of a matrix. So these are the major linear algebra programs. So, well, to demonstrate a few of them, linalg determinant on A gives you a determinant, of course. Inversion, inv gives you inversion. Now, the nice thing is that, again, if you use matrices, then inversion has a very nice symbol. It's just dot I. Okay, so you can imagine that the code looks much nicer when you can use dot I rather than inv. Okay, so this is another nice perk of the type matrix, because the code looks way nicer. So whenever you take the inversion, you just type dot I. Otherwise, you need to use the inv. Okay, so eigenvalues, eigenvectors, eigvals, as I said before, this gives you eigenvalues, which in this case, the matrix is not Hermitian, so the eigenvalues are in general complex. Now, if you do Eigvals H, it will give you real eigenvalues, huh? But these eigenvalues are wrong. They're not, they don't correspond to this matrix. So what has happened here? Can you guess? So whenever I use the routines for symmetric matrices, then the code LAPAC assumes that matrix is either upper diagonal or lower diagonal. I think by default it's probably upper diagonal, and then just takes the upper diagonal part and assumes that matrix is symmetric, and then works as it would work on symmetric matrices. So basically, the eigenvalues have to be real, isn't it, for symmetric matrices? Okay, so what else can we do? Yeah, solve. Basically, solves a system of linear equations. So if A is a matrix 3 by 3, B is some vector B, then this would solve A times X is B. And then we can check that if we multiply A times X, minus b, we'll get some small number. Of course, then this value x times a times x minus b is not exactly 0, but with the numerical error is 0. So 10 to the minus 16 is good enough for us. Okay, so this is most of linear algebra that we had in mind. So there are other routines which are sometimes useful. So sum, cum sum, trace, diag. So sum does the usual thing. It sums the array. Cum sum does the cumulative sum, isn't it? Cumulative sum of the array. Trace just takes the trace of the array, and diag takes the diagonal of a matrix. So pretty self-explanatory. So sum of a vector produces the sum. Cum sum produces cumulative sum, so which still needs to be a vector. Trace, of course, produces a number on the array. Diag takes the diagonal values of the array, and then sum of diagonals has to be the same as trace. That's another way of computing trace. I think trace is actually does exactly that, sum of the diagonals. Okay, so what else? The other thing which is useful is so-called reshape routine. So reshape is extremely useful because you wanna many times look at the same array as a one-dimensional array or n-dimensional array, because obviously in memory everything is one-dimensional, and sometimes you do want to have the one-dimensional equivalent of the array. Okay, and for this, reshape is really useful. So original array A is 3 by 3, but we can reshape it into 9 by 1. Or turns out you can reshape into any size as long as the number of items is the same as the actual array size. So in this case, 3 by 3 has 9 items, so we can't do anything else but taking the, oops, my computer froze. Oh, now it's better. We cannot do anything else but 9 times 1, okay? Because 3 by 3 doesn't allow anything else. But reshaping in general can be into any shape that uses the same amount of data, correct amount of data. Now, one thing that it's important to remember is that now we are changing here the data which was reshaped. So we are changing AG, and AG is actually something, it's the reshaped data of A. So we're changing the reshaped data, and then we are printing out not the reshaped data, but the original data. Okay, so we're taking the original data, we are reshaping it, then we are changing the reshaped data, and then we are printing the original data. And lo and behold, we see that the original data was changed as well. Okay, so what that tells you is that the reshape function is efficient, which means that it's not going to create a local copy. It doesn't create a copy of the array. It actually uses the same array. It's just a different view on the same array. Therefore, reshape is extremely efficient. Okay, so it's just a different view on the same array. However, flatten is another routine that does similar thing. So flatten of any high dimensional array creates a one-dimensional array out of any dimensional array. So if A is 3 by 3 or any other array, it will create just a one-dimensional array AX. However, if you change array after you flattened it, you will see that the original array is not changed. Okay, so what does that mean? Well, very simply, it means that flatten is not as efficient. It actually creates a copy. Okay, flatten creates a copy while reshape does not create a copy and uses the original array. That's the difference. Okay, finally, vectorizing functions. This is something quite useful. So if the functions are simple in the sense that you, for example, square something, or you take sinus or cosine of an array, then these type of functions are already vectorized. So if you have temperature, which is the third column of my large array, and if I want to calculate the square of this temperature, all I need to do is to square the array, and this is going to be, every component is going to be squared. Okay, so kind of obvious. Now, this means that this operation square is vectorized. It's already vectorized. Okay, and I can use it equally well on numbers as on arrays. Now, if I want to calculate cosine of temperature, that would also work. Okay, so which means that cosine is also a function which is vectorized. And of course, I can construct pretty complicated functions, cosine of square of whatever, and or logarithm maybe, and this is also vectorized. Okay. Well, logarithm of temperature is not good because temperature can have zeros in there, and then logarithm doesn't know what to do. But anyway, this is still okay. So in the sense that as long as you're using functions which are vectorized, you will get things work on the entire array. Okay, so of course, if the functions were not vectorized, you would need to iterate over the array. Okay, this is a slow way of doing square, is that you have to iterate over the entire temperature and create a new array, which is very slow, while the vectorized function, applying it to an array, is very fast. Now, the question is the following. Let's say that we have a function which is not so easily vectorizable. So what comes to your mind, for example, is a theta function. Okay, so theta function says that, well, for positive values return 1, and for negative values return 0, for true and false. Okay, so theta function is a function which is not that easy to vectorize. Why? Because, well, if sentence doesn't work on arrays. Okay, so if you do theta of temperature, it will say, I don't know how to do that. The true value of an array with more than one element is unclear. Okay, so, and this is pretty common. I mean, you write just slightly more complicated code, and you will get a result which cannot work directly on an array. Okay, so what do we do in this case? Well, Python provides something. It's called vectorize. So as long as the function is not too complicated, Python will be able to vectorize a function. So all you need to do is to give us an argument. You need to give a function which takes as an input a scalar variable, such as x, floating point, for example, and it will know how to create a function that can be used on array of such items, array of floating points, for example. So you call vectorize, and then you save this new function, which is vectorized function, and then then you can apply the vectorized function on your data. That works. Okay, and you get all the positive temperatures. Okay, so whenever in the data the temperature is positive, you get 1. Whenever the data temperature is negative, you get 0. This is how theta function has to work on data, for example. Okay, now let's say that you want to calculate number of days in each year with positive temperatures. So how do you do that? Well, you take first positive temperatures, and then you create array of Boolean expressions out of this. So you typecast 0 and 1s into true and false. Okay. Well, this creates the mask, isn't it? Our mask. Then we can use mask on our original data, and well, we just see which days have a positive temperature. Okay, so kept means all the data which have positive temperature. So next, we enumerate all the years which appear in the list. So the years which appear in the list are from 1800 to 2012. Actually, 2000, the data that exists is between 1800 and 2011. But they're after 2011. So it means that the very last value is just an epsilon less than 2012. Okay, so it's basically including the last day before 2012 is included. So therefore, we need to iterate up to 2000, up to less than 2013, and then these are all the years that are that exist, and then you can use something which is called histogram. Histogram will actually create how many well, it creates a histogram of the data, isn't it? So creates a histogram of data and will tell you how many days in each year had a positive temperature, isn't it? So histogram, you give x component is the data that has positive temperatures, and then we look at the bins. So the bins are either 1800, 1801, 1802, 1803, 1804, and so on. And then the histogram will actually check all the, will collect all the entries which fall into that bins, isn't it? Okay, so and here we are plotting now the histogram of how many positive or how many days will have positive temperature in all these years. Okay, and as you can see, this data does go up a little bit, maybe. So maybe we will see some hint of global warming, maybe. I don't know. Maybe it's just a speculation. Okay, so this is all about NumPy. We are done with NumPy, and we can go now to SkyPy. Is there any question on NumPy subjects? Or it's too simple? Simple, huh? So let's go to SkyPy. So again, if you want to follow yourself and check yourself this code, you can download from either GitHub or you can download from our webpage. So on our webpage, Physics Rutgers EDU 509, you can download here SkyPy, or you can download from GitHub the original document. Okay, so SkyPy is so great because it contains so many different routines for science that are essential tools for creating our codes. Now, people accumulated all the knowledge from many decades of work, and both from Fortran and C and so on, and they created libraries for Python. So including special functions, which we already touched upon. Integration is very powerful. As we will see, it has one-dimensional integration, two-dimensional integration, and even three-dimensional integration. So that's actually quite non-trivial to write yourself. One-dimensional is easy. For example, you probably tried in your at some point yourself to write routine to do, let's say, a Simpson's rule or trapezoid rule. That's quite simple. But doing this in three-dimensional, it's kind of quite non-trivial. Now, optimization has all kinds of root finding routines and minimization routines. Then interpolation, not just simple one-dimensional interpolation. It even has two-dimensional, three-dimensional interpolation, and moreover, it has all the tools for those splines, which are very nice. Then Fourier Transform, it has the fast Fourier Transform, for example, which is also somewhat non-trivial to write yourself. Linear algebra we already saw. Then it has a support for sparse eigenvalue problems, various statistical things, multidimensional image processing, and input-output. We already met this input-output, which is basically load takes state. All this is now, well, many of these things are actually ported to Numpy now, including input-output and including linear algebra. They're both appearing now in Numpy in the newest versions. Okay, now here I'm explaining again the same thing that I explained last time. So in the past, we were typically, if we want to import everything that is in SciPy, which is convenient, we would just write from SciPy import star. But in the newest version of Python, it turns out that this creates a lot of warnings because SciPy has several symbols which appear also in Numpy, and those from Numpy are kind of preferred. In particular, linear algebra is one such thing, and input-output is another such thing. So therefore, this is a hack to import Numpy after SciPy, so everything is all written that exists in Numpy as well as SciPy. Yeah, here I decided to use linear algebra for SciPy, but again, for practical purposes, they're identical. So you can use either the one from Numpy or the one from SciPy. They both give you the same thing. Okay, so the demonstration, we're going to first include Basal functions. So there's a large number of mathematical special functions which are important in physics, in science in general. So if you want to see all the entire list of special functions, there is an enormous list. So area function, elliptic functions, Basal functions, zeros of Basal functions, faster version of Basal functions, integrals of Basal functions, derivative of Basal functions, spherical Basal functions, Riccati Basal functions, stew functions, and there are many, 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 many others. Okay, so error functions, Legendre functions, so too many. Okay, so lots of special functions, and well, my experience is that if they don't exist here, then probably you will not find the code yourself either. So pretty much every special function exists in SciPy. Okay, so now how to include them? Of course, you could say from SciPy special import star, but if you want to import only some special functions, you can write which one. For example, Basal functions and what is this? Yn are the second type of Basal functions, Neumann functions, and then zeros of Basal functions or zeros of Neumann functions. So now, if you just want to print particular Basal functions of any 0, x is 0, no problem. You just use it like this. We're using this Python 2 types of printing. So Neumann function and Basal function at 0 or 1 look like this. Now we're going to print the Basal function. So as you remember, there's this very special symbol, $matplotlib inline, which allows inline plotting inside this Jupyter notebooks. Then we are going to import pyplot from matplotlib. This is how they advise us now to do, not to use pylab directly, but the pyplot from matplotlib. And then in addition, we are going to import also image from IPython display. This is going to be used later on to import an image from Wikipedia. This is not very important right now, but we're going to use it later. So this is not essential. Okay, so we're going to do this. Then we can plot Basal functions. First few Basal functions, let's say J0, J1, J2, J3. So what did we do? Well, we plot n's between 0 and less than 4, isn't it? And then we just take some linear mesh between 0 and 10, 100 points, and then we got the Basal functions of particular order n and array x. So what this demonstrates to you is that when you evaluate Basal functions, these entries can be arrays. So basically x can be array, not only a number, and also n can be array, not only a number. As far as I remember, you can have either n to be array or x to be array, but I'm not so sure if both can be arrays. I think not, but actually I don't know. I think not, because then in principle we could get an output two-dimensional array of Basal functions, but I think this probably is not supported. Okay, but definitely if you give one-dimensional array of abscissas of x values, then you give you get out one-dimensional array of Basal functions. And then all that we've done here is we use so-called label in matplotlib. So label, if you write label and then a string, an arbitrary string, it prints legend like this. Okay, J0, J1, J2, and so on. Okay, and the legend was constructed on the fly with this dollar operation. That's something that we discussed before. This is the way you create strings strings with using arbitrary integers, floating points, and so on. Okay, so once we have the label, then we have to call something which is called legend. So legend is something that will actually display the labels. So without this, we are not going to get the labels. Okay, even if the labels are remembered or they're written down without doing legend, it's not going to appear. And then the good idea is to write legend location is best, because then it means that Python will try to put the location in the best possible way in the plot. You can of course fine tune where exactly the legend is supposed to appear here if you want to. You can even create legend which can be moved with a mouse. That's actually very useful for your own graphics plots. Before you submit this to a journal, you sometimes want to optimize the position of legend so that you can create the graph as small as possible. And in this case, floating point legends are actually very useful. Okay, so there's some little plotting. I guess it's pretty trivial, but yeah, more interesting things. So we can do numeric integration. Numeric integration is contained in a SciPy integrate, and general purpose numeric integration is contained into quad, double quad, and triple quad. In addition, of course, to this general purpose integration, we also have all standard integrations like Simpson's rule and trapezoid rule and what is it, Rombeck rule, all those. So if you know something about those different rules, sometimes if you have data, it's a good idea to use the best rule that works best for your data. For example, if the data is very smooth, then you should use a higher order integration routine. So if the data is very smooth, probably Simpson's or Rombeck rule is very, very good. But if the data is not smooth at all, then the best you can do is to use trapezoid rule. Non-smooth data, trapezoid rule the best. Now, this is if you have a data. But if you have a function, however, then you can use this general purpose integrators. This is for the functions. Okay, we specify the functions. So let's say that we import all those integrations. So quad, general purpose one-dimensional, double, three-dimensional. Of course, you can always do help on those, and you can get the idea of what the input needs to be. Now we are not going to do this. We are going to just use quad function on some functions. So the first argument of quad has to be a function, then has to be the lower boundary and the upper boundary. Quite obvious, isn't it? So we are going to integrate now lambda function, which is just x squared. So this is one way of creating function on the fly. You remember we were discussing lambda function last time. So we are creating lambda function x squared on the fly, and we are integrating x squared from 0 to 1, which has to give you 1/3 with some estimation error bar 10 to the minus 15. Yeah, these integration routines are nice because they give you not only the value, but they will also give you the absolute error, estimated absolute error of your integration. Now, of course, this integration is not very, it's not that appealing. However, let's say that we want to integrate something more complicated. Let's say that we have a Basal function, yn of t, and we want to integrate not just Basal function, but Basal function divided by t, dt from 0 to x. Let's say that that's what you need. Okay, so there is some, we will later on see something similar. It's needed in solving the Schrödinger equation. So let's say that this is what you need. So what are you going to do? Well, we can create on the fly, we can calculate the function, which is exactly this, yn of t divided by t. And to be a bit fancy, we're going to allow both t and n to be generic. Okay, so t and n, so the function that we are going to integrate will have two arguments, t and n. Now, the important point is that this variable over which we are going to integrate has to be always the first variable. Okay, otherwise it will not work. So the first variable has to be the variable over which you integrate. That's something that you have to remember. Now, in addition to this variable over which you integrate, you can have several other variables if you want to. You might not want to have them, but you can have them. Okay, it's allowed. Now, if you have them, then you have to specify them through so-called arcs tuple. Okay, so this is a way. So if you add arcs and then a tuple, it means that you're specifying here all the rest of the variables. Okay, so once more, here we have one more variable. Therefore, I need to specify through the arcs all extra variables. So let's say I have here 3 more variables, not just n, but n and m. Then I need to give 2 tuple of 2 variables, extra variables. Okay, that's very useful because sometimes you don't have a function that has only one variable, but might have several. Okay, so that's a standard way that you do it. However, the important point is that the first variable always has to be the variable that's actually used for the integration. Okay, that's not arbitrary. This is how it needs to be. But there can be optional, extra optional arguments which you specify through arcs. Question?
Yes, actually. First off, what exactly is lambda? And then secondly, how are R's defined here? I'm having trouble following.
Okay. So first, we discussed last time what lambda produces. Lambda produces a function. So let's say Tn, lambda Tn is Jn n t divided by t. Okay, so we are producing f2, let's say. This is a function. We could specify exactly the same function, let's say f3, in this way, Tn return Jn and t divided by t. Okay, so these two functions, f2 and f3, are identical. So you remember, lambda is something that creates function on the fly, inline function. Okay, so it's a word that tells you that this will create function on the fly. Okay.
Okay, I remember that now.
Okay, so therefore, what we did here is we created a function on the fly. Okay, the one that we needed. However, the problem is that this function, well, let's say m here, which m is not necessary, but fine, let's say it's m, that's another one. Okay, so now the problem is that this quad needs a function, let's say f2 or f3, maybe easier to remember, needs a function, but this function, unfortunately, is not ready for integration. Why not? Because how are you going to integrate something that has requires three variables? Okay, integration requires one variable, isn't it? So Python would get confused. You can't integrate something like that, okay? Because f3 needs three variables. Now the workaround is the following: the first variable has to be the one over which you integrate. Okay, has to be. However, if you have more than just the first one, if you have some extra arguments, then you can specify them through so-called args parameter. Okay, and you have to give the value then of the rest of the variables.
So, Professor, is it actually assigning the value 1 for n and the value 2 for m?
Exactly, exactly right.
Okay.
Yeah. So so it's going to be easier to understand. So import integ, let's say, from Skype I import integrate, and let me show you help integrate quad. Okay, so it specifies that you can have something which is called args. Okay, and this args has to be a tuple of optional arguments which we need to be passed to function, and function is of course our function. Okay, so that's what I try to explain. So function, you see, it can have this form, double x. Okay, that's the simplest one. However, it can have this form, double x, and any other stuff, user data. Or it can have double function integer n and some data that I don't know exactly what it is. But the point is that this is the usual form. So it gives you the first variable, gives you x, and then some user data, and this user data here has to be specified through the args. And that's exactly what we're doing. So we have some extra arguments, nm, whatever, and then we have to give a tuple for these things.
May I ask?
Yes.
Like with the last homework assignment, we had Z and alpha in there, and we were just defining it before we actually executed any line of code. In this case, you would just stick them in args.
Yes, you stick them in args, yeah, but you have to, because in this case, because you see, the problem is that otherwise you have to redefine F3. Yeah, so of course, if this is your function, you could still do it. I mean, you could say globally n is equal to something and m is equal to something, okay? And then you omit these variables here. Of course, that would work, but that requires you to redefine the function. Many times you don't want to redefine the function. I mean, it's a complicated function, you don't want to do it. But of course, that's the workaround.
I think I understand it now. Thank you.
Okay. Yeah. So yeah, and then okay, so this integrates. Now that we understand this, okay, so now I copied the same thing here. It's the same code, so lambda function, and then args is ns, and ns is given here as 1, and then the only difference here between this code and that code is that we are doing this for many x values. So x is a linear mesh between some very small number, not exactly 0, because 0 would be a 0 divided by 0. So some small number to, let's say, 30, 300 points. So we are creating now linear mesh between 0 and 30, 300 points. We are discussing Basal function of order 1. And then we have this nice routine that creates an array with this integration of Basal function divided by t, 0 to x, and its function of x. Okay, so we are creating this, and then we're plotting it. Fs. Okay, so now again, this is a plot of integral Basal function of t divided by t from 0 to x, and x goes from 0 to 30. Okay, so this is a fast way of creating such a plot. And later on down there, we're going to try to find all values where this function crosses 1. So as you see, this is oscillating function that reaches 1 several times. Okay, and let's say I want to calculate 0. So we want to figure out where this function crosses 1. There are many solutions. Okay, and let's say I want to calculate this. We're going to do this later on in Python, which is very easy. If you want to do this in C, the same type of code, first you need to have an integration routine. Second, you need to have a routine that finds zeros, and this is just way too much work. Okay, but in Python, it's just few lines. So that's beautiful. Okay, but before we do that, we want to discuss more general integration. So let's say that you want to integrate something, you want to do the 2-dimensional integration. So for purposes of demonstrating this, we're going to use just a simple Gaussian, e to the minus x squared minus e to the minus y squared. So it's just a simple Gaussian. And we're going to integrate Gaussian between 0 and 10 and 0 and 10. Okay, so this we can do even analytically if you want to, but just to demonstrate. Now, there's the double integration function also needs function of 2 variables. If there are 2 variables, then we don't need to specify any arcs. But if you have more than 2 variables, then you need to add arcs, isn't it? Just like before, this extra variables which might appear. And then the syntax is that you need 4 additional variables, which are the minimum and maximum of the outside integral, and then minimum and maximum of the inside integral. Okay, now you have to remember that the inside integral could be a constant or could be a function. Okay, why? Well, this should demonstrate here. I mean, the inside integral can be a function ya of x and yb of x. Okay, so when you have a 2-dimensional array, of course, in general, you're not integrating over a square, but you can integrate over something much more complicated, in which the inside limits depend on the outside variable, and therefore you can specify here a function, generic function, which is not a constant, but it's a function of x. Okay, clear? And in order to do this, we are using again the lambda function because it's convenient. We could, of course, define these functions outside somewhere and then use them, but this is just for convenience. Now, I mean, in this case, it's actually not necessary because we are using ya and yb as constants. So we are creating functions which return constants. Okay, that's not needed. We could easily do this. It would work as well. Why? Because actually it turns out that this double quad allows the upper borders to be constant. Okay, that's fine, completely fine. But this is not generic. This thing is much more generic, isn't it? Because you can have you can have the inside borders which depend on x. Both work in this case. Okay, that's because double quad allows both constants and non-constant limits. Okay, so well, next chapter is a little bit more interesting. So we're going to discuss ordinary differential equations, and in particular, we want to solve this problem of double pendulum. So for this, we need this image. So this image actually just loads an image that's on the Wikipedia page. Okay, so if you execute image and then you give a URL from somewhere in the internet, you get image from that page. And this shows you a double pendulum. So what we're going to do next time, because it's 6:20, what we're going to do next time is, well, obtain the equations of motion for double pendulum, which we are supposed to be able to do ourselves. When was the last time that you managed to write them down? Can we still do that? Okay.
Before last semester.
Okay, you can do it? I'm not so sure if I can do it, but okay, supposed to. Okay, so anyway, we're going to write them in Hamiltonian formulation, not in Lagrangian, but Hamiltonian formulation. And well, then code and hopefully get the simulation. Now, in addition to this, I prepared. Well, turns out that somehow to me unknown reason, it's very hard to get simulation done inside Numpy. No, inside Jupyter. So doing simulation in usual Python is actually very easy. Okay, so this requires just a few lines of code. Okay, and it's pretty nice simulation. But if you want to do the same thing in Jupyter, somehow I couldn't make it work. I don't know why. I can give you this for the homework. you put this, you make the simulation inside Jupyter. I tried, I failed. Okay. So anyway, that's the motion for the double pendulum. Looks pretty realistic, huh? Okay, so any question? Any question?
I actually have a question about something that we did at the end of last lecture, so I can wait till afterwards.
Okay, that's fine. Any other question? No? If no, then thank you very much for today. I guess we see each other on Monday. Okay, have a nice weekend. Bye.
See you.
Mm.